Hello all. Today we will see numerical based on the heat load calculation, which is also known as cooling load estimation. This problem is very important in the field industrial field to know the how much load is gained by the heat into the room, and this problem is very much important to design a air conditioning system to a particular room or space. Now in this numerical we will see how we can get the total heat load into the room if we are having a single room which we are given. So now moving toward our sample problem. This problem is taken from a book, standard book RS Kurmi. Now here in the problem given as a laboratory with a dimension of 30 meter by 30 meter into 4 meter high, which is to be air conditioning. So we have to design our air conditioning system to this dimension lab. Now the 30-meter wall faces towards the north. The north wall has two doors, 2.5 meter and 3.5 meter dimension each. So now area of a wall is given, area of a door is given, which is 2.5 into 3 meter. Now the south wall has a four glass windows, 2 meter and 1.5 meter each. Uh, they have given that the south wall has four windows, which is glass. Now the east and west walls are also have four windows with the same dimension. The lightning load is given, which is 15 watt, which is unit of fluorescent per meter square area. Now the infiltration is given, which is one air change. We simply take one air change normally in our problem or any situation. If in a particular case, if we are given the separate air change value, so we have to take that. Now the solar heat gain factor, which is given for the south, east, west glasses are 150, 50 and 350 watt per meter square respectively. Now what is sensible heat gain factor, which is total heat gain from the sensible heat gain from the solar light into the room, that is called as sensible heat. Now the overall heat transfer coefficient for wall, roof, floor, door and windows are given as 2.5, 2, 3, 1.5 and 6 watt per meter square Kelvin, which is also denoted by U. Now the corrected equivalent temperature differences are given for walls and roof and floor, which is 12, 15, 12, 17, 20, 2.5 centigrade. Now these are the corrected equivalent temperature difference. The temperature difference between the outside and inside wall, that is called as equivalent temperature difference. Now there are capacity of person are given, 100% are there, and sensible heat and latent heat is given 75 and 55 watt each. Now the ventilation requirement is given, which is 0.3 meter cube per minute per person. This is normally a fresh air required for a person. The outdoor condition which is given is 43 degrees Celsius dry bulb temperature and 0.0277 kg per kg of humidity ratio. Here two conditions are given, which is dry bulb temperature and humidity ratio. Generally two conditions are required or sufficient for drawing the point on the psychrometric chart. Now the indoor condition are also given. We are required 25 degrees Celsius dry bulb temperature and 0.01 of humidity ratio inside the room. It is required. Now they have said that use factor of 1.25 for fluorescent light. So here we are given fluorescent light is 15 watt, so we have to take just 1.25%. So we have to add 25% here. Now they have said that they determine room sensible heat load and room latent heat load with the 5% safety factor, 5% fan power, 1% leakage of supply air, and 0.5% heat leakage to supply air. They have also mentioned here uh, safety factor and also leakage and other factors that we have to add into our heat. Now here in the solution we can see a sample drawing of the room or schematic. Now here four walls are shown. At the north wall there are two doors with the dimension of 2.5 and 3.5 meter each, and temperature difference is 12 degrees Celsius. At the east wall four glasses windows are there of dimension of 2 meter by 1.5 meter, and solar heat gain factor which is 50 watt per meter square, and temperature difference is 12 degrees Celsius. And at the south wall, the solar heat gain factor which is 150 watt per meter square, and temperature difference is 15 degrees Celsius. And at the west wall, the dimension are same, and heat gain factor is 350 watt per meter square, and temperature difference which is 17 degrees Celsius. Now this is our schematic of our problem. Now moving toward the given data. So we have to write down all the data which we have in the problem. So these are the listed down here. So you can see. Now here we have shown fresh air by V1 which is 0.3 meter cube per minute required, which is volume flow rate is given. Now the area of door is given 2.5 into 3 which is 7.5 meter square, and area of one window which is 2 into 1.5 is equals to 3 meter square. Now here we have to draw one table in which we have to calculate heat of each component or element in the room. So now here sources are as north wall, south wall, east wall, west wall, roof, floor, doors, windows. Three wall have windows which is south wall, east wall, and west wall. Now in the second column we have our heat transfer coefficient which is U in watt per meter square per Kelvin. Now area we have to take, dimension we have no, so we have to just calculate area of door and wall and other things. Now in the next column we have to put equivalent temperature difference. So from the formula UA delta T we can calculate the sensible heat gain. So from this component we will get sensible heat gain. So for the first which is north wall, we have 2.5, and area we have to reduce the area of door from the wall. So total area we will get 105 meter square, and temperature difference is 12 degrees Celsius. Now here sensible heat factor in watt we will get as 3150 watt for the north wall. Similarly for the south wall, east wall, and west wall we can calculate. Now for the roof dimension we have 30 into 20, so simply we will get 600, and temperature difference is 20, so we will get 24 kilowatt sensible heat gain from the roof. Similarly for floors, now we have to calculate the same for the door and windows. Here we will get total heat gain which is 44788 watt, which is nothing but 44.788 kilowatt. So in this table we will get the values of a sensible heat gain from the room. Now other components are also there, like air change, fresh air is coming into room, so that will also add a heat. Also leakage is there, so and other factors such as humans, lights, and other electronic component. So we have to calculate all this heat coming into room. Now this is clear. We have got the sensible heat gain which is 44.788 for the room. It is only for the room. So now solar heat gain through a south wall. We have a sensible heat gain, solar heat gain factor which is given to us. Now we have to calculate the solar heat gain. Solar heat can come from walls also, and from the glass windows also, or door also. But here they have mentioned that the solar heat gain from the windows, as the solar rays coming from the windows, so it will add some heat into room. So that we have to calculate. For the each wall they have given separate solar heat gain factor, so it would be separate for each direction. Now from the south wall we will get 1800 watt. Similarly from the east wall we will get 600 watt. From the west we get 4200 watt. Now the total solar heat gain which is sensible through the south wall, east wall, and west, that come up 6.6 kilowatt. So we have added these three values. Now the total sensible heat gain from the person. We have 100% in the room, and sensible heat which is given for single person is 75 watt. So now 7.5 kilowatt sensible heat gain from a person, and the total heat gain from the person, total latent heat gain, 55 watt is the latent heat gain from a single person, and there are 100%, so we will get 5.5 kilowatt. Now temperature difference we are having for a glass window which is 18 degrees Celsius. Here we have to calculate now, air is coming into room. Here they have given the air changes is 1. So how we calculate the airflow? The formula is LWH into air change. LWH, which is dimension of a complete room. Volume of a room multiplied by air change divided by 60. So we will get into in form of minute. Now we have got 40 meter cube per minute as volume flow rate of air into the room. Now that air will also add some heat into room. So that sensible heat gain due to infiltration air, which is 0.02044 volume flow rate into temperature difference. That is the standard formula. We will get 14.7 kilowatt of air of heat added by air. And latent heat also, the formula is 50 into volume flow rate into humidity ratio difference. Humidity ratio difference we are given in the problem. So we have to just put here 0.0277 and 0.01, and we will get latent heat gain from infiltration air is 35.4 kilowatt, which is more. Here we know that the volume of ventilation air from the outside air, which is fresh air required, which is 0.3 meter cube per minute per person, is given. So for the total person, which will come out 30 meter cube per minute. Now we have to calculate outside air sensible heat and outside air latent heat. Outside air sensible heat we will get 11.04. This formula is same for the as like infiltration. Just we have to put value of air into fresh air in terms of volume flow. So here you will get outside air sensible heat and outside air latent heat. Now sensible heat gain factor due to lightning, we can calculate. We have given 15 watt from each light. So and they said that add factor of 1.25. So multiplying we will get 11.25 kilowatt from air. Sorry, from a light. Here we have to get we have to put here a use factor. Use factor is generally what, how much type in a day we are using that light or component. So here it ranges from 0 to 1. 1 indicate complete use, so we will take 1. Assuming that fan is placed before the conditioner, so negligible factor 5% for the power. Here we have to now calculate the total room sensible heat in the table, and in the from the windows solar heat gain and other airs from the heat gain from the air that we have calculated. So we have to just add them. So completely we will get uh, so here we have added a factor of 1.065. So from where it come, that they have said that we have to add some factor into it, which is safety factor and also fan factor, and it's all this. So that completely comes around 6.5%. So that is generally 1.065. If they have not mentioned the factor, so generally we will take 1, and there is no need to multiply by any factor. Just we have to add all the hits, so we will get room sensible heat. Here room sensible heat comes out 102 kilowatt total room sensible heat, and now similarly we will get room latent heat, which is 71.6 kilowatt. Now till now we are having the room sensible heat and room latent heat from the total room sensible heat and total room latent heat. Here total room latent heat, which is 71.6 kilowatt, we know, we have calculated now. Now if the fan is located after the conditioner, then 5% of fan power should be added. Then room sensible heat will remain unaffected. So 5% is added into factor 1.065 plus 0.005 and into total heat. So sensible heat will be 107 kilowatt. In the previous we will get we have got the 102 kilowatt. So now here we just have to add fan power if it is placed after the air condition. And in here we have taken the case as fan is before the air condition, so we have to neglect the fan percentage. So in this way we can calculate the total heat gain in the room and total latent heat gain. So that's all for now. So in this way we can calculate the total heat, sensible heat and latent heat which is coming into room, and from this we can calculate our total heat or total cooling load. That is our total cooling load, which is comes out 107 kilowatt and 71.6 kilowatt.